Hello folks! Well, the last of the data types that I want to go through for the course are pointers or references. So we'll go through and talk a little bit about the two of them, and we'll start off with the distinction between the two. If I can just remove that. So the idea is that we want some way to be able to refer to an item indirectly. So whether we've got something that's been created off in the heap and we need some way to keep track of where it is, or whether we're creating objects and we want some way to refer to them, or whether we're explicitly playing with memory addresses and saying, I want to look at memory address whatever, or I want to look at the memory address of this particular item. So pointers are the more memory-focused idea, where we've got the actual, or at least the virtual memory address of an item, and we can look in memory at that spot. So we can get memory addresses, we can look at memory through addresses. References are an abstraction of that, where we're saying, okay, I want to provide a mechanism that allows the programmer to access something indirectly, but I'm not going to let them see the real memory address or the virtual memory address. I'm just going to say, here's a variable that refers to this thing. You can get at it through this variable or through this reference. So it does allow a little bit of information hiding, implementation hiding. The programmer, in the case of references, doesn't get to see the memory addresses, doesn't get to play with the memory addresses, doesn't get to see the implications of those memory addresses. And that allows the implementer of the language a little bit more flexibility in terms of how they create things, how they make things happen. And it also protects against cases where programmers deliberately or accidentally misuse pointers and wind up messing things up because they're actually playing with memory. It is more an assembly language level of thought typically to deal with the memory addresses themselves. So C and C++ are a little unusual in giving you that ability to directly play with addresses. So pointers are powerful, but that gives this associated risk that you safeguard against with our references. So in terms of uses, you've all played with most of the aspects of this. It does give you a way to dynamically create things in the heap, whether that's explicitly through programmer control, whether we're using things like new or malloc or calloc, or whether it's implicitly happening, whether the language is creating a new object somewhere off in the heap for you every time you ask for one. But it does allow you to create things on the fly and allow those things to be cleaned up as the program's finished with them. It gives you a means for passing references or pointers to an item from one subroutine to another, so that you don't have to explicitly copy the entire item back and forth. If I want to pass an object to a function, then here's a reference to it. Just follow that link essentially, and you'll be able to access all of the data for it. It lets you avoid actually copying field by field or item by item everything that's inside whatever's being passed around. That does also give you the ability to distinguish between passing something by value and passing by reference, passing essentially a copy of something, or passing a reference to it where you can actually get at that item and potentially make changes to the item. So that's going to be both good and bad in that it allows for the possibility of side effects, which is either desirable or undesirable, depending on what you're trying to accomplish. And again, it gives you the ability to exchange these pieces of information back and forth without the need for creating duplicates of something and the time and memory complications that come along with that. So in terms of the use to access things dynamically, to create space in the heap and be able to get at it, this is what gives us the ability to have something that is not resident in the stack, something that doesn't begin and end when a function call is made and when that function call completes. It allows us to exchange information across the lifetimes of different functions. All right, we can create it in one function, pass a reference to it back or return a reference to it, and everybody else can use that reference until you're finally done with it, and it can be deallocated. So there has to be some kind of a means of communicating where that item was created. And then presumably some kind of a means of getting rid of it once you're finally done with it. Right? If it's not on the stack, its deallocation isn't automatic anymore. We have to have another mechanism for saying, we're done with this thing, it's not in use anymore, get rid of it, remove it from the heap. So that can either be taken care of automatically, right? So this will be the case in most languages that use references, where since the programmer isn't explicitly creating it, they're not explicitly getting rid of it either. And since we're not playing with the memory addresses, somewhere behind the scenes, the language is taking care of that for us. Or it can be done explicitly, right? New and delete, or malloc and free, or whatever your combinations happen to be, where the programmer is taking care of both the creation and the destruction of the item. Gives the programmer more flexibility, but it also gives them more responsibility in that they have to do these things. They have to know the syntax for it, they have to follow it through, and they have to deal with the possibility of memory leaks and wild pointers and following null pointers and dangling pointers and all the other wonderful pointer problems that come along with it. And in fact, one of the big reasons that modern operating systems split programs by memory, where they segregate memory across programs, and give programs access to virtual memory so that although it looks to program A like it's got full access to memory, it's actually seeing something different than program B. Program B's it essentially has its own copy of virtual memory, distinct from programs A. They can't mess up each other's memory. And it's precisely because so many problems come up from these issues of wild pointers, dangling pointers, memory leaks, memory problems created by dynamic allocation and deallocation. So we're going to look into the mechanics of garbage collection, of freeing this stuff up automatically, and look into the mechanics of how you actually allocate that space in the heap. How do we find some place in the heap to give to the programmer to use for whatever item they've just created? So we'll dig into that a little deeper in another week or so. Now, one of the things that often comes as a bit of a surprise to people is the idea that we have to associate, or we frequently do associate, a data type with a pointer or with a reference. And the idea is, really, this is just a memory address, right? It's just referring to a location somewhere in memory. Why do we need to associate a data type with that? And the idea is that once we actually use a memory address, once we use a pointer or we use a reference, what we're left with is we're looking at some spot in memory, and we have to know how much is stored there, right? How many bytes of memory we're going to be looking at, and we have to know what the bit patterns stored there represent. And if you take any given bit pattern, it means something differently if you treat it as a string than if you treat it as an int. So we have to know what kind of data it's actually representing. And the idea of having a typed pointer is that the type associated with the pointer says, okay, look at this memory address and treat the thing there as if it was an integer, or treat the bit pattern that's there as if it was the beginning of a string. So you will find that with typed languages, you often have typed pointers or typed references where you're saying, okay, here's one of these things, it's of this data type. If you allow the programmer really wide access, really generalized access to play with memory addresses and to look at what's in memory and treat it as whatever type they want, then you can start running into all kinds of type checking issues. And this is one of the things that we see in C, where you're able to use things like unions, and you're able to cast pointers and say, okay, well, here's a pointer to an int, treat it as if it was a pointer to a string. We're able to look at memory and treat what's stored there as a different data type than what we put there originally. And of course, this totally messes up any idea of being able to perform strong type checking in your language. Right? If the programmer can totally bypass and say, well, I know I stored it as an int, but treat it as a string anyways, then there's absolutely no way you can provide strong, reliable type checking. And that's one of the reasons why C is regarded as a very weakly typed language. Okay, in terms of the things you can do with pointers, Now, a lot of this stuff is going to happen implicitly with references as well, but I want to look at the mechanics for pointers because they give us a little bit more power and they introduce new issues. If we're going to support pointers, then obviously we need operations like being able to take the address of something. I want to look up the address of variable x and store it in a pointer. And we need to be able to go the other way around. I've got this pointer, I want to look at what's in memory at that location as if it was an int or as if it was a string. So you need these abilities to take an address and dereference it. Presumably you need operations to be able to copy pointers across. I want to copy, pointer x into pointer y. I might want the ability to compare two pointers. Do pointers x and y point to the same thing? It might be reasonable, with stick kind of a question mark on there, to say I want to be able to compare two addresses numerically beyond just saying are they equal. Maybe you want to be able to say, well, is x stored earlier in memory than y or later in memory than y? So maybe a less than greater than makes sense. Where things get really interesting is where we start allowing pointer math. If I take the address of something, so you give me the address of x, am I allowed to add 4 to it, effectively an offset, and say, okay, what's that offset 4 or offset -4 from the start of x? It makes sense when you're dealing with structures and arrays and things. I want to look this many bytes into this complex data structure to get at a specific element or to get at a specific field. But if you provide that kind of power, does it let you essentially look anywhere? I want to take a look at, I want to get the address of parameter A. And then I'm going to look forward and backward using offsets and see what's in memory around that parameter. Right? See what the next parameter is, see what the previous parameter is, see if I can figure out where the local variables are, see if I can go even further and find the beginning of the next stack frame and see what its parameters are. Right? If I allow generalized pointer math, I can start doing all sorts of weird and wonderful things. It also brings up issues in, can I just take a number and an integer value and use it as a memory address? If I know that I've got 6 billion bytes of memory, can I say, well, I want to look at what's in memory at address 2,012,000? So is that something that we're going to allow in terms of pointer operations? And what does it mean? If I have an array, for instance, and I do something, if I take the address of the start of the array and I start doing pointer math like x plus 1, is that saying look 1 byte further into the array? Or is that going to do something for me like, okay, well, if you want to add 1 to that array, it's an array of ints or 4 bytes, I'm going to add 4. So effectively, I'm giving you a way of saying, okay, the pointer math is going to take me this many elements forward or back. So those are some of the things that you have to consider where you're looking at how pointer math is handled in a particular language. So as we've done with a couple of the other data types here, what I want to do is have a little bit of a play in C or C++ and see how it's actually working in the language that we're playing with. So where have I got this? I think this is in pointers.cpp. So let's take a look in there. Again, this is in the same directory as the code for the rest of the slides. So this one's pretty straightforward. All we're going to do is create a long integer, pointer to it, and then we're going to try a little bit of pointer math with it and see what happens. So you can see we're storing a value of 5 in our variable L. We're storing the address of L in a pointer. We're just printing that out. And then we'll try a little bit of pointer math. If I add 3 to the address of L, does it just add 3 or does it do something more complex? Does it say, okay, well, let's look 3 longs further down in memory? So we'll take a look at that first. And let me just make sure everything's up to date here, and we'll try running this beastie. So in this particular case, we've gone through, we look at we're printing L, we're printing its address, and then we're saying, okay, if I use P++, if I do an increment on it, where's it pointing? Well, we see the address has gone up by 8, which we know by now is the size of a long. So doing a plus plus is effectively saying, let's increment the pointer by the size of the kind of item it's pointing at. So this is pretty much tied to the idea that usually we're using pointers in this kind of case as some way of stepping through arrays. So it's thinking, this is probably this pointer is the start of an array of longs, and so when you do a plus plus, you just want to look at the next long along the chain. So it's adding the size of the item pointed at. Similarly, in the case where we said, okay, let's add 3 to P, let's take a look at what happened. We went from address 98 to address B0, again, obviously in hex. And so B0 minus 98 in hex is 24. So again, if we added 3 and it bumped us up by 24 bytes in address, it's adding essentially 8 for each one. So again, it's incrementing by the size of the item times whatever it was you tried to add. So that is something useful to think about when you're playing with pointer math in C or C++. The second half of that little program was we went through and created another variable. We stored a character string in there, so hello world. And then this is an example of bypassing the type checking in C or C++. Where we're saying, okay, we've got this character array that's got this hello world string in it. Let's take the address of it and cast it to a pointer to a long. So we're saying take the address of the string and treat it as if it was the address of a long. And then we'll go through and print out what's there in memory as if it was a long. So there's going to be some bunch of bytes representing hello world. And then we're going to go through and say, okay, well, let's take a look at those bytes and see what they represent as a long. And that's what you see down here. Right? This great ugly long is basically saying, okay, well, let's go to that spot in memory, go to the spot in memory where hello world begins, and just start treating those bytes as if they were the beginning of a long. So it takes those first 8 bytes, says, here's what that is as a number. And again, this is an example of where you totally bypass type checking. Right? It doesn't matter what great principles you had in mind. The programmer is totally capable of taking anything you've got in memory and treating it as something else by performing the typecasting. So these are the kinds of issues that are raised by allowing low-level access, right? Allowing pointers, allowing the knowledge of memory addresses and the manipulation of memory addresses, right? Supporting that at the programmer level. Really flexible for the programmer, really powerful, but it can wind up being really dangerous. All right, that about wraps up our consideration of data types. So where we will get to next is to start looking at control structures. We'll start looking at blocks, if statements, loops, that kind of thing, and then we'll move on to look at subroutines and implementations in that way. All right, and we'll see you next time.